Part of Hilbert's eighth problem was to ask for a proof, or otherwise, of the Riemann hypothesis. Now, spoiler alert, we've still not done this, but there is a $1 million prize attached. So the Riemann hypothesis concerns the behaviour of the Riemann zeta function, but I'll start by talking about its baby brother, the zeta function. This was introduced by Leonhard Euler, and like any function, it takes a number, we'll call it s, and it maps it to another number. And in this case of the zeta function, it does this by taking the infinite sum, 1 over 1 to the power s plus 1 over 2 to the power s plus 1 over 3 to the power s, and so on. So if s equals 1, you just have the harmonic series, 1 plus a half plus a third plus a quarter, and so on. And this series doesn't converge, it just blows up. So mathematicians consider its value as undefined. But when you take s equals 2, you get the series 1 plus a quarter plus a ninth plus a 16th, and so on. And this does converge. It settles down on the value pi squared over 6, as Euler showed. Interesting to see pi cropping up here. But for Euler, this zeta function was only defined, it only had a warranty, if you like, when s was greater than 1. But 100 years later, Riemann comes along, and he says, I'm going to jailbreak this function. I'm going to do two things. Firstly, I'm going to let it take complex numbers as inputs. So now it's taking a point on the complex plane and it's mapping it to another point on that plane. Worse than this, he says, I'm going to let the real part of those complex inputs be less than 1. How does he do this? How does he wander into the there be dragons territory? Well, in the place that the function is well understood, we have mappings that take complex numbers to other complex numbers, that transform them in the complex plane. And these transformations make a pattern, and that pattern can be uniquely extended into the there be dragons side. So now we have all that, we can say what the Riemann hypothesis is. And it's simply that the places where that function, the Riemann zeta function, evaluates to 0, apart from some trivial zeros that we won't go into, all of those places lie along the line where the real part is 1/2. This is called the critical line. And why does this matter? Well, if you can prove this, you can prove tons of things. In fact, there are hundreds, if not thousands of numbers that have been proven contingent on this being true. In particular, it tells us something very profound about the way that prime numbers become sparser as you get to larger and larger numbers, how they thin out. It tells us exactly how that happens. But we've still not proven it.